In this video, I will discuss practical aspects for the kinematic analysis of triple junctions. So first, we will start with a system which only has two plates and one boundary. So we will talk about the velocity condition for this boundary between plate A and plate B to be stable. So let's discuss, or let's introduce the velocity vector of A relative to B. This is vector UAB. There's a velocity vector for B relative to A, UBA. This boundary here will be stable if UBA plus UBE is equal to 0. So it means that UAB is equal minus UBA. That's a condition for two plates. So let's go a bit further about the meaning of stability. So the stability means that after a little increment of time, the net motion of the boundary is 0. So let's go forward in time and compute the displacement of A with regard to B. So we have velocity vector UAB times an increment delta t. This would be the distance that of motion of this plate with regard to this one. If we make the same for the plate B, it's moving with velocity BA within an increment delta t, and it's making this displacement delta x BA. So we make the sum of these two displacements and you will get 0. So that's the same, so that's the kinematic condition. The net motion is 0. This boundary is stable. If we move to the case with 3 plates, so now we have a system with A, B, and C. And you can recognize from the symbol that these are ridges. So we have one ridge marked by the 2 lines, a second one and a third one. The first thing we want to do, we need to identify a point on each of the plates, and we need to see how plates move, or how points move relative to each other. So we have the point A located on plate A, a point B located on plate B. Since this is a ridge, the motion is divergent, so A is moving away from B, and B is moving away from A. Now, let's introduce a third point on plate C. Again, we have a ridge between A and C, so C is moving away from A, and A is moving away from C. The same can be done for the boundary BC. This is also a ridge, so B moves away from C, and C moves away from B. That's step number 1. Then we will link the points to create the triangle ABC. Now we add the plate boundaries. So let's add plate boundaries AB. It is a vertical line that is marked now. It has a right angle here. Let's add boundary AC. It has again a 90 degrees angle and it's cutting through this face. Now we do the last one, UCB, and we draw this limit. It has a right angle to the BC segment, and it crosses through the triangle. What we can identify now is that actually the 3 lines intersect. So yes, they do intersect here, and this basically means that the triple junction is stable. So graphically you can determine this. So we have a triangle, and we have different relative velocities of plates, and so we have the velocity of A relative to C, that's UCA, and it will be marking these edges of the triangle. We have the velocity of B relative to A, that's UBA on that side, and the velocity of C relative to B, that's UCB. Now we introduce the stability condition. The sum of these three vectors is 0. So one thing we want to discuss is the azimuth. So that's the definition of an angle, and it's one angle which is measured clockwise from the north to the position of an object, for example, to a ridge. So these are all azimuth angles which are given on this diagram. I just make a quick example of how an azimuth is measured. So we have the system here with the 3 plates. The north is pointing to the north, and we have the velocity of B relative to A. It's 90 degrees to the north here, so it has this position. We have a ridge here which is located a bit further down here, and we will have this 90 degrees from this ridge. We will have the motion towards plate C from this ridge here. So what is the azimuth of CB, UCB? It will be 90 degrees here. It will be 110, so that's the azimuth from here to there, 110 plus 90 degrees, because the motion from a ridge is at 90 degrees. Okay, so it's 110 plus 90 degrees. That's how to compute an azimuth. Now we have a problem which is very close to what you will have to do in the exercise. We want to compute the magnitude of a velocity vector, knowing the value of two angles. This one is called alpha minus 180, and this one is 70 degrees. And we know the length of two sides, so we have measured two velocities, UCB and UBA, which we have with different magnitudes. How to compute UAC? There is a rule called the cosine rule. So that's an extension of Pythagorean theorem for non-rectangular triangles, for general triangles. The length of this sides of the triangle is squared is the sum of UBA square plus UCB square minus 2 times UBA times UCB times the angle, or the cosine of the angle, which is opposed to the segment of interest. Okay, so we have the angle in front of UAC is the angle of 70 degrees, which is known. So this we know. UCB and UBA we know. These are the two velocities we know. So we can compute UAC. In this example, UAC would be 100 millimeter per year. 104. Now, we would like to compute the azimuth alpha of the third ridge. So alpha is here on our diagram. For this, we can use the sine rule. So the sine rule, it allows us to equate some ratios. And the ratio is, for example, the sinus of this angle divided by the length of the facing segment is equal to the ratio of the sinus of this angle divided by the length of the facing segment. So we can set up this equality, and then one can solve for alpha. And here we obtain alpha is 226 degrees. A last step of training about triple junction would be to consider this picture here. we have a system with 3 plates, A, B, C, and they all slide past each other. The question is whether this is stable or not. So that's a transform, transform, transform tripole junction. So let's do the exercise together. We have C that moves south with regard to A, B which moves away from A and C, and B moves away from C, of course. We construct the triangle that links the points. And now we will add the plate boundaries with the angle here. You see that the plate boundary that separates A and C is a straight line. So it goes along the face of the triangle. C moves with regard to B along this boundary. So you see it's a bad start already. Then we add the boundary BC. B moves with regard to C along this boundary. And then we add the last boundary UBA, and we again along the face of the triangle. So in this case, we see that the lines, they never intersect all together inside the triangle. The transform boundary is hence not stable, and it's always unstable. So that's it for the exercise part. I wish you good luck with the exercise.